So in order to understand what the graphs of the secant function and the cosecant function look like, we have to understand first what the graphs of sine theta and cosine theta look like. And since we already saw that cosine theta and sine theta were periodic functions that were just like waves, radio waves, or whatever they might be, that peak at 1, they have a maximum value at 1, and they have a minimum value at -1, then we should be able to also use that information to be able to find out what the graphs of secant theta and cosecant theta are going to look like. We'll start off with this identity that shows us that how secant theta and how secant of theta and cosine of theta are related to each other. So secant of theta is always 1 over cosine theta. Now, just to see what that really means, it's basically saying that no matter what angle you provide me, right here, that when you plug in that angle, the value of secant theta is always the reciprocal of the value of cosine theta. So the value of secant theta is the reciprocal of the value of cosine theta. So notice that when we're graphing functions, we're just simply graphing all of the corresponding outputs for each of the corresponding angle inputs. So let's recall, first of all, that cosine of theta is somewhere in between -1, the lowest it ever is -1, and the highest value that we ever get is +1. So I'd like to just draw a quick little table to show us the relationship between these values. I've picked a few different values here for cosine of, or for theta. We're just going to evaluate each of the cosine theta values, right? So when I'm again, on the unit circle, cosine of theta is the x coordinate. So at the angle of 0, the x coordinate is 1. And at the angle of pi, the x coordinate is -1. Well, if you take a look at the reciprocal of those values, it's no different for secant of theta. So it looks like the maximum and minimum values for sine and for cosine of theta are also going to be the exact same thing as the maximum and minimum values for secant of theta, because the reciprocals of 1 and -1 are 1 and -1. So let's take a look at pi over 2. Now at the unit circle, 90 degrees, pi over 2, cosine of pi over 2 is going to be 0. And 3 pi over 2 is going to give me a value as well of 0. Okay. Well, if I take the reciprocal of 0, be very careful, because notice that the reciprocal of 0 is actually undefined. And so when you're taking a look at the graph of cosine theta, there are no breaks in the graph. It's continuous from -infinity to infinity. But apparently when we look at the graph of secant of theta, there's going to be a couple of locations where the graph is undefined. Undefined on a graph typically is represented by a vertical asymptote. We're also going to see that by the time we get around to 2 pi, we're still at a value of 1. And so the reciprocal is 1. We just got back to where we started. But I want to look at a couple of other values here. Most notably pi over 3 and 2 pi over 3. If you think about the angle of 2 pi over 3, it's a steep angle. So the x coordinate is small, the y coordinate is large. And so that implies that for the angle of pi over 3, cosine of pi over 3 is 1/2. So we know the cosine of pi over 3 gives me the value of 1/2. And 2 pi over 3 in the second quadrant is going to give me a y value of -1/2. So remember that when you take the reciprocal, you're simply flipping the fraction here, and the reciprocal of 1/2 is now 2. Notice how 2 is bigger than 1, because when I take the reciprocal of fractions that are less than 1, I will always get values that are larger than 1. More specifically, we see that at 2 pi over 3, if the y value for cosine was -1/2, now we see that the y value is -2. So it looks like if we were to create a table for these values, we'd start to realize that there's some really interesting things that start happening here. where when I take the values of, let's say, cosine theta giving me 1/3, secant of theta will give me 3. If cosine of theta is 1/5, secant of theta is 5. So anytime you take fractions that are between -1 and 1 and take the reciprocal, you get values that are either larger than 1 or less than -1. So what that implies then is that secant of theta will have to be always less than or equal to -1, or the value of secant theta will always be greater than or equal to 1. And so we want to be able to determine what this means for a graph. So let's take a look at Desmos. We see that this is the graph of cosine of x. Okay. The reason we know this is cosine x is for a few reasons here. First reason is it starts up at 1 at the angle of 0. At the angle of 2 pi, it hits the value of 1 as well. Halfway in between, it hits the value of -1. And then at pi over 2 and at 3 pi over 2, it hit values of 0. Right? So this is the value, the graph of cosine, but we should realize that cosine is infinite. We want to take a look at what secant theta would look like, but let's go ahead and come up with a list of a few points that we can plot here for secant theta. So first of all, I know that if cosine of 0 is 1, then secant of 0 will also be 1. So that point is going to be on the secant graph. Okay. I also know that by the time I get to pi, my y value for cosine is -1. So the reciprocal is also -1. By the time I get to 2 pi, I see that the value is back up to 1 again. And so the value for secant of theta will also be 1. But we also want to pull out a couple of other points. Let's plug in pi over 3 from our table. Remember that when we plugged in pi over 3, cosine of theta at pi over 3 is 1/2. So let's look where that is real quick. So cosine of pi over 3 is 1/2. But I'm trying to look at the graph of secant theta, so the reciprocal is going to give me 2. Interesting, because it's above 1. If I plug in 2 pi over 3, I could see that my value for cosine is -1/2, so the reciprocal would be -2, so that's on the graph. And if I were to continue by just plotting 4 pi over 3 and 5 pi over 3, because those are also unit circle angles that are easy to plot, 5 pi over 3, then when I get to 4 pi over 3 in the third quadrant, I know that I'm also going to have a cosine value of -1/2, so secant is going to be -2. And if we end up plotting that 5 pi over 3, we see that in the fourth quadrant from 3 pi over 2 to 2 pi, the value will be +1/2. So secant will give me a value of 2. Now this seems really peculiar here, but I want you to also realize that by the time I plug in pi over 2 and 3 pi over 2 and -pi over 2 and -3 pi over 2, all of these values for cosine are 0. So when I take the reciprocal, they're going to be undefined. So let's go ahead and look at what secant looks like. Secant is this function. Look at how this curve goes through all of the indicated points that we expected to occur. Asymptotes. But if I were to zoom out a little, you could see that there are in fact asymptotes. And so the graph of cosine is literally only used in order to come up with the graph of secant. So if I can plot the graph of cosine theta, then I should realize all of the zeros of cosine theta become asymptotes for secant, and all of the values for cosine theta being 1 and -1 are going to be the maximums or minimums of secant theta. So let's take a look at how to graph this by hand. Well, in order to graph either any secant function or any cosecant function, the first thing we're going to do is to graph their corresponding reciprocal function. So the first reciprocal function we're going to plot here, we're going to say is y equals 1 here and y equals -1. Okay, and we're going to plot cosine of x. So keep in mind cosine of x starts at the y-axis at 1. And by the time it gets out to 2 pi, it's back to where it started. So we're going to plot 2 pi at 1 as well. Now cosine of x reaches a minimum halfway in between. So I know that that minimum at pi is going to be at -1. And we should see that from our unit circle as well. And now we should notice as well that the zeros are going to occur halfway in between 0 and pi and 2 pi, which is why this is going to be pi over 2 and 3 pi over 2. So when you look at this graph is, going to be this little hump here. And that's 1 period for cosine of x. We want to plot y equals secant of x. So the great part about being able to graph secant is that once you have the important values for cosine, anywhere where there used to be a 0 is now going to be undefined. So each of those values are undefined, which means that secant will have asymptotes. So the first thing we do is we plot our asymptotes. Make that straight. Better. There we go. And at 3 pi over 2, secant of theta will also have an asymptote. Now, if you remember from Desmos, when you look at each of these minimums and maximums, this minimum for cosine turned out to be the maximum value for sine. So I refer to these as hills and valleys. So we're now just going to be plotting our hills and valleys getting close to these asymptotes, which makes sense because if this is -1, any value here is going to be less than -1. So the reciprocal will be on the other side of -1. And so notice that we're going to do the same thing up top. Realize that if this is a maximum for cosine, then it's going to be a minimum for secant. So each of these graphs is extending towards the asymptotes, and finally this maximum here is also going to extend over here. Now what we don't want to do is start to draw the other one yet, because we don't have what the other value is. Now if you plotted back to -pi over 2 and you drew the actual asymptote, then you'd have somewhere to go. But we don't want to do that at this point unless you end up extending your graph. So the last step here is delete the cosine graph, and there's your answer. So in fact, you don't really even need to plot you don't even need to draw this blue graph to begin with. All you really need to do is plot the 5 important points, and the graph of secant x will be the asymptotes with these hills and valleys. So let's take a look at sine x. Sine of x is going to be something really similar. So remember that sine of x is different from cosine x in the sense that instead of starting at 1 at the angle of 0, it's going to start at the origin, because sine of 0 is equal to 0. Which means by the time we get out to 2 pi, I'm also going to be at the value of 0 because they're coterminal. Halfway in between at pi, we're also going to be hitting 0. But notice that sine of x, as sine increases from 0 to pi over 2, okay, we should realize that the values of y, or the values of sine x, increase up to 1. And then they decrease, and by the time they get to 3 pi over 2, the values of sine of x are now at -1. And again, the unit circle shows us this if we were to look back to the notes from the graphs of sine x and cosine x. So this right here is our graph. It starts at the origin, it curves up, it comes down, it comes back down to, that's ugly, I want to redo that. It curves up, reaches a maximum, curves down, reaches 0, continues to curve to reach the minimum, and then curves back up to 2 pi. So there's a graph of sine x. But in order to graph cosecant of x, for the same reasons that we graphed secant of x over here, we should recognize that any of the values of 0 are now going to be asymptotes. Now the values of 0 are at 0, pi, and 2 pi, when for secant, those values were at pi over 2 and 3 pi over 2. So let's put our asymptotes each place where there is a x-intercept or a 0 for sine x. Notice that these are going to be at different locations than the graph of secant x, simply because sine and cosine are 0 at different locations. Now, we technically don't need to draw one on the y-axis, but you're able to do so if you choose to. And now we just realized that anywhere where the y value is 1 for sine x is going to be the same thing for cosecant x, and likewise for -1, it'll be the same. But now we have 2 asymptotes for this to get close to on both sides. We now know that this one is the graph of cosecant x for the minimum. And now look at the minimum for sine x, and it becomes a relative maximum for cosecant of x. So if we were to now just get rid of each of these pieces here, get rid of the cosine graph, these are the graphs of secant x and cosecant x, but notice that the only way we really were able to graph this was by first graphing sine x or cosine x. So for any function that involves secant or cosecant, you just simply graph their corresponding function, and the very last step is to draw your asymptotes and your hills and valleys. I refer to this as a valley, and I refer to this as a hill. Okay, just because it looks like a hill and it looks like a valley. Okay, so notice that at this point, let's go ahead and take a look at a function involving transformations, something that we actually did in the last lesson. And now we're just going to graph the corresponding cosecant or secant function. So this is an actual graph that we graphed when we were learning about cosine functions. So the first thing you remember we did was that we recognized that this was our angle, which we referred to as theta. Okay, and we know that the standard interval was from 0 to 2 pi. So now we're just figuring out where is x plus pi over 3 going to actually be bounded. So we subtracted pi over 3, and we got our initial and final values. And then we ended up just taking each of the midpoints of that in order to find all of the additional values by cutting each of those values in half. And once we did so, we ended up saying that this had an amplitude of 1, and it shifted down 1. So instead of it starting up at 1 and ending up at 1, I know that it's now going to start 1 unit below that. And so this is the same transformed function, cosine function that we graphed in the last section. But what we'd like to do at this point is delete the cosine. Let's say that we were now asked instead to graph secant of x plus 3 minus 1. Turns out that we do it the exact same way. The only thing that's different is that we don't graph the cosine function. Once we have all of our important x-axis values, once we have all of the important locations where cosine would be graphed, this is where we're now going to graph the secant function. So take a look at this. The only difference now is that because this graph moved down 1, we're not looking at the x-intercepts in order to put our, or the zeros here in order to put our asymptotes. We're putting the asymptotes at this new midline, because those are the new quote unquote zeros of the function. Pi over 3, if I plug in pi over 3, okay, or rather negative pi over 3 here, notice that there's a few values that are going to be 0. Sorry, this is actually pi over 6 here. So let's just say we plugged in pi over 6 just to see what happens. That would mean that y is equal to secant of pi over 6 plus pi over 3, which is 2 pi over 6, minus 1. So notice that y is equal to secant of 3 pi over 6, which is actually pi over 2, minus 1. And secant of pi over 2 is undefined. So that's why notice the values here, the asymptotes, are not going to be at the zeros of the function, but instead they're going to be at where the new midline is going to be. So we can draw our asymptote here at pi over 6. And we draw another asymptote at 7 pi over 6. Okay. Now you can delete that midline, because that midline, sometimes it looks like it's an asymptote, so I really want to make sure that we see it's not an asymptote, it's just there to help us to graph. And now we're ready to graph the rest of our function. So we can start with the value over here at negative pi over 3, and that used to be the maximum for cosine, now it's the minimum for secant. This also used to be a maximum for cosine, so it's another minimum for secant. Now we have to scroll down a bit so that we can have something to get close to, since we ended up having this shift. So we should go down a little further here so that we can now get close and see that this right here is the maximum for secant, and therefore come down to here. So the graph of secant of any function, as long as I know how to graph cosine, the secant is the last step where we just fill in our asymptotes and our hills and our boundaries. Cosecant will be taken care of in the exact same way. So to take it one step further, let's assume that we end up having a secant function, or perhaps we have a secant graph. Now, typically we would not have these points because those points are not actually on the asymptotes, but those points were just there to help us to recognize that they were in fact the new quote unquote zeros of our cosine function that was shifted. But now if I wanted to determine what is the graph of this function, I should be able to replot these points. Okay, replot these points right at the midpoint of the maximums and minimums. And if I draw this graph to connect these dots, I should recognize that it is sure enough a cosine function. And because it's a cosine function, I know that the blue one will be secant. Then I could just take my time to recognize that this graph must have shifted left pi over 3 because it was at x, or because it started at negative pi over 3. And I also see that there were a couple of zeros at some of these locations here, so I should be able to fit this to a cosine graph. So whenever you're trying to look at a graph and determine whether or not it's a secant graph or a cosecant graph, turns out that you could actually make it either one, because sine and cosine are the same functions, just shifted off by pi over 2. But this would be most easy to graph, or to create a secant function, simply because by connecting the dots, it looks mostly like a cosine. Okay.